Greetings. Welcome back to AP Physics C, Electricity and Magnetism, where I'm covering Unit 4 over magnetism. And this video, Chapter 4, is on a very specific thing. It's called the Biot-Savart Law. And in the last video, we talked about a simple way to figure out the magnetic field due to a very specific case, a long current carrying wire. But unfortunately, that doesn't always apply to every situation that we would need to find the magnetic field for. And so the way around that is through this law, the Biot-Savart Law. So let's jump into it. So when I say that our previous method of finding magnetic field had some limitations, that's because of two very important considerations we had to make when using that equation. So it's only accurate under certain conditions, meaning if we're to use this equation, mu naught I over 2 pi r around a current carrying wire like this one, that equation is only going to hold if the wire is perfectly straight and if the wire length, L, is significantly greater than the distance that some point P exists from the wire. So this distance R right here would be the main indicator. If either of these two conditions do not apply, then we cannot use this equation. So what do? Well, in general, say we have a weird curved wire like this one, and there's some point P in space. If we want to find the magnetic field at this point P, we do technically have the tools to do so. We just have to think a little bit small and start implementing some calculus. So to determine the magnetic field at that location, the first thing we need to do is do what this picture down here is indicating. Split the wire into a bunch of tiny segments, all of length dl. Now, obviously these dl's here aren't nearly tiny enough to make the integral work in the way it does, but this is the general procedure you need to think of. You just pick a random point on the wire. Now, the direction of these little segments, dl, is aligned with the direction of the current at that location, which you can imagine, if it's curved, to be kind of like tangent to the curve at all points. Now, the next thing you need to do then is treat that tiny wire like any other. And the magnetic field dB is given by this equation down here, which is the equation that AP gives you on the formula sheet. Now, obviously, each point dl along this line is going to have a slightly different variation of this formula because they'll all be different distances away from the point, or they will all have different directions, or maybe even the current is different in certain instances. We don't know. But this isn't intrinsically set up to allow for those adjustments if you can set up these variables like dl and r in terms of what you're moving through in the wire, like many other integrals that we cover in this class. Finally, we'll take all of those dBs and add them all up, and you can probably guess how exactly we do that. And that is with the Biot-Savart law, which basically takes that infinitesimal magnetic field formula and gives you the integral to add it all up. So this law was empirically modeled by Jean-Baptiste Biot and Félix Savart in 1820, pretty early on. And this law is basically the most general approach you can get to finding magnetic fields. So the basic idea here is you take that dB term and, well, you add them all up. And so the main thing that the Biot-Savart law adds is this little integral right here, just indicating that, well, if you want to find the total magnetic field, you got to add them all those terms. So a lot of these terms are pretty familiar, but there are some newcomers to the mix. So the main thing here, mu naught, is the permeability of free space, or the vacuum permittivity, vacuum permeability. That constant is going to show up again and again and again, and really anytime you need it, you can always find it on your formula sheet. The current I is also present, and it's kind of assumed in this equation that current is something that isn't going to change with the length of the wire, but of course, with integration, if there's a will, there's a way with accounting for things like that, if somehow it were to happen, but it's unlikely, considering our circuit rules. Then inside of the integral, you've got all of your things that are likely to change. So the first one is dl, that's the infinitesimal length of the wire. And again, this is basically going to be so small, it's nigh incomprehensible, because that's the best way to get an accurate result of the total, with constant changes in the direction and the distance from the point P. Now, this infinitesimal length dl is cross-producted with this little newcomer here. This is called the distance unit vector, and it's a vector that has a magnitude of 1, so it doesn't really add anything numerically to the equation, but its main purpose is to serve as the direction carrier for the distance from the wire down here. So R and R technically are the same thing, but it's almost like R is astrally projecting its direction onto the numerator of this equation, just so we don't really have to fuss with it being squared down here. Now, this equation technically has a different form if you didn't have this unit vector here, but AP doesn't give you that one, and frankly, this one is a little bit nicer to deal with for most of the cases that AP asks you to try and solve. So it's worth keeping in mind that this unit vector R is the distance from the length of wire to the point P. It has to go in that direction. If it's not, then things are going to go wrong horrifically. Now up here, there's this little picture just to aid with a little right-hand rule that we can use for this. This is technically the third right-hand rule that we have used so far in magnetism, but it's really the same formula as any other cross-product right-hand rule. So you get your right hand, and if we're looking at this picture up here with DI and R, the idea is, or sorry, DL and R, the idea is that you align your index finger with the first term in the cross product, so that would be DL, off this way, and then you align your middle finger with the direction of R, which is the second term in the cross product, so that would be out this way, and then if you stick your thumb out, that of course gives you the final direction of the product at the end, which is magnetic field. And in this case, if you set everything up right, you stick your index finger out in the direction of DL, you stick your middle finger out in the direction of DR, your thumb should point into the screen in this case, which is the magnetic field direction. Makes sense. And with any cross product, that general formula can be used. It doesn't matter what it is. If it's a cross product, it's normally A index cross B middle finger equals thumb result, whatever that may be. Now it's worth noting that this formula, unlike the other one, actually does provide the magnetic field as a vector quantity because, well, a cross product produces a vector quantity as a result, as opposed to dot products or just general formulas whose purpose is to only find magnitude. Now, the good news is, even though this is a cross product, most of the examples that AP expects you to solve, and most common examples applying Biot-Savart Law in general in introductory physics classes, involve DL and this R unit vector being perpendicular to each other by default. And if those two are perpendicular to each other, not only does that make your right-hand rule resolve a little bit nicer, but it also means this formula technically can be simplified a little bit, so it's a little bit less intimidating. If DL and R are perpendicular to each other, that just means that the other form of this, DL times R times sine of theta, automatically just becomes DL at the end. Because if these two vectors being crossed are perpendicular, then, well, R has a magnitude of 1, sine theta will also resolve to 1 because the angle between them is 90 degrees. And so all that's left as a result is the vector DL. And so technically a slightly nicer looking version of the Biot-Savart Law would be this one here, where we've gotten rid of that unit vector, we've already considered it, and everything kind of obliterates to 1 except for DL. So this is worth keeping in mind. And again, most of the scenarios we'll be looking at are going to involve this. So with that, I'm going to show you two examples that are probably the most common approach of the Biot-Savart Law. And there are more that you can investigate, but these two are likely to be the most common, as anything else is typically a little too time consuming for most scenarios in the class. However, I may cover some of those additional examples in later videos as their own standalone. So with that, I'm going to cover two examples, both of which involving loops of wires. So let's get going. Okie dokie, let's get going with this first example. Here we have a semicircular arc of wire carrying a current in what looks like the counterclockwise direction. And the wire carries some current I through it. So this is a nondescript current, just a variable. So this will be a symbolic question. Now, the wire has a radius r. The fact that this is a capital R implies that it is going to be a constant radius. So this is something that we can treat as a constant. There's no need to vary the distance r in this case. So our goal is to use the Biot-Savart Law. Microsoft Word doesn't like the name Bio for some reason, to derive an expression for the magnetic field strength at the center of the arc, down here. Now, another common version of this problem is for it to be a full circle. So we could just as very well take our result here and multiply it by 2 in order to get the magnetic field strength at the center of a circular arc of wire. So the first thing we should do is probably write out the Biot-Savart law. So let's do that. Our Biot-Savart law is going to be B equals mu naught I divided by 4 pi times the integral of dl cross r all over r squared, where really I like to just use the vector notation for r here, but you can also give r its fun little hat like that. How whimsical. Now, again, here, the first thing you should look for is an excuse to get rid of this gross looking cross product right here. So let's try that. Now, in our lay of the land over here, we have our segment of wire DL kind of already laid out for us. It's off this way, like so. And if you look at the distance from R to that location, let's say right here, well, it's looking like the circle is always going to be, or the tangent of the circle is always going to be perpendicular to the radius, which makes sense. Tangent in the context of a circle is always perpendicular to the radial direction. So in this case, we do have a 90-degree angle between DL and R. So we can go ahead and get rid of that cross product. So we'll go ahead and rewrite mu naught, our equation, as mu naught I over 4 pi, it rhymes, times the integral of dl times sine theta, or a sine of 90 degrees, let's just say, over r squared. And of course, that's just going to eliminate the sine 90, so we only have to worry about dl in the numerator at this point. Now, before we continue, another thing that can be pretty nice is, well, in this case, with any circular arc, typically the length dl is going to be turned into an angular quantity. Recall that with a circle, you can always define the length along the circumference of a circle as an arc length, which in this case would be L equals R times, let's say theta in this case, like so. That is, by definition, arc length. Now, because we need an infinitesimal L, well, an infinitesimal L would still have the same radius R, but the angle inside would be d theta, or in this case, in the picture, it seems like it's already spelled out for us, it's d phi. So out here, we'll say dl, little l in this case, is equal to the radius R of the circle times d phi. And that is our infinitesimal arc length. Now, the purpose of fitting that in is that probably the most convenient way to integrate through this circle is by integrating across half of a circle. So from like 0 to 180 degrees, or from, I guess if we wanted to set up our bounds, it would be 0 radians to pi radians out here, based on our unit circle. So I'm going to finish writing this as mu naught I times, divided by 4 pi times the integral of, and I'll go ahead and plug in my arc length over here, R times d phi divided by r squared, which was there before. Now in this case, we can splunky out one of the r's on the top and the bottom, and so we're just dividing by one singular r. So the last thing we need to do before we can integrate this, because it doesn't really seem like anything varies with angle except just the infinitesimal phi, I suppose, is to figure out our bounds. And in this case, we've technically already discussed that. So we're going to start, let's say, at the right side of the circle, just because it's aligned with the 0-degree mark. And we will just rotate counterclockwise through this circle until we reach pi on the other side. That would take us through half of a circle. So our bounds here are going to be from 0 to pi. Remember, when you're integrating through an angle, you always want to integrate over radians, not degrees. The math works out completely differently depending on which one you use. And so here, what we'll do, we'll take our official integral here, mu naught I over 4 pi times the integral from 0 to pi of d phi over r. But of course, r is a constant as well, so we can technically move that out of the integral without any issues. And so we're really just integrating through phi here. And so integrating this function, we get b equals mu naught I over r, over 4 pi r times just phi by itself from 0 to pi. And by plugging in our bounds with the fundamental theorem of calculus, we get our final result of mu naught I over 4r, as once we plug in this pi for phi here, we're going to have a pi that cancels out with the one that's already present in the formula, almost here, since I didn't write it anywhere else. So this right here is our final answer. This would be the magnetic field strength at the center of a semicircular length of wire. Pretty cool, pretty simple, despite how much I've hyped up the Biot-Savart law being scary. All right, let's look at another one, also involving a loop of wire, but this time a little bit more complex. Now for this next example, the main thing that we've changed is that now we've taken point P basically from the center of a circular arc and moved it out along the x-axis here off center. So now we have a diagonal distance from the radius of the wire to the point P, as opposed to simply being the radius of the loop here. That's going to add a few extra hurdles that we need to climb over in order to get to our answer. So let's take a look at the information we've got. We know that our loop has a radius r that we can use, and it carries a current I. We can also use that. And it's a known distance x from the center of the circle. So all of those quantities are in play. Now, we have a little clarification here for our own convenience, just to clarify the perspective that's going on here. And that's that at the top of the loop, the current is flowing out of the page. So the current out here at the top is represented by a dot. And so then it's going to loop around, travel downwards here, and then it will be traveling into the page out here, represented by an X. I will actually go ahead and distinguish that with a different color, because we will want to distinguish between the top and bottom to help figure out any symmetries that are going on here. So our goal, of course, is to determine the strength and direction of the magnetic field at point P. So the first thing we need to do is probably work out the direction. Let's draw our vectors so that we have an idea of what we're actually adding up in this case, because this one's a little bit less obvious. So in order to do that, we're going to make use of our right-hand rule. And I'm going to start with this magnetic field produced by the current at the top of the loop up here. So with our right hand, we're going to stick out our pointer finger out of the page, so in the direction kind of towards my face. And then you'll stick out your middle finger and point it, rotate your hand until it points in the direction of R based on the picture out here. And then if you stick out your thumb, it should be pointing in the direction of the magnetic field, which is in this case perpendicular to R and pointing kind of up and to the right, which is a bit of a strange direction for a magnetic field. So if I drew this to the best of my ability, the magnetic field vector would be pointing like this, kind of up and to the right and explicitly perpendicular to R. With a cross product, remember that the product is just as perpendicular to the other two vectors. So if dl is perpendicular to r, which it is in this case, then the magnetic field strength here is also going to be perpendicular to the distance r. Now in this case, we can also take a look at the bottom and see what changes about the direction. Now for this one, we're going to again stick out our right hand. In this time, we're going to point our pointer finger in the direction into the page. And then in this case, it's going to help to draw the distance r here. But in general, you're going to take your pointer finger and from the bottom of the loop, or rotate around until your middle finger points from the bottom of the loop up to point P, which is going to be about that way. And then if you stick your thumb out, it should point down and to the right, also perpendicular to this direction. So I will go ahead and draw the distance from the bottom of the loop to point P, like so. And then the direction of the magnetic field here, again, is perpendicular to that line, down and to the right, like so. So both of these vectors indicate a magnetic field strength, and the main difference is their direction. Otherwise, everything else is pretty consistent. So it's at this point that we need to decide what's going to cancel and what's going to add up. Because if we can make our lives easier with figuring out directions that we don't need to bother adding up due to cancellation, then it will make this problem a lot shorter and a lot easier. So in this case, what I notice is that the magnetic field, at least in the x direction, does seem to be adding up in basically regardless of where you are around the loop. If you were to take your hand and move it really in any other direction, odds are it's still going to point at least a little bit in the x direction and then outwards in some y or z direction in this case, like with the top and the bottom here. Now, with all quantities being equal, that implies that the y direction of this magnetic field up here is going to cancel out with the y direction of this magnetic field down here. And in the z direction, we'll assume that it's probably going to be the same thing. So in this case, the main thing that we can utilize is the fact that all components are going to cancel except bx. Or in other words, really the only direction that we need to integrate through is the direction involved with the x component of any magnetic field vector dB. So with that out of the way, let's go ahead and write out the Biot-Savart law. And really here, we don't need to worry about anything except the x direction. So I'll set up the Biot-Savart law specifically for the x direction. So total bx is going to equal mu naught I over 4 pi times the integral of dl cross r hat over r squared. And since it's the x direction, let's say we're defining this angle here as phi, then it would be the cosine of that angle phi. And we will leave that as a problem for ourselves later to figure out exactly what that angle is. I'm sure it's findable. Now again, let's look for an excuse to get rid of this cross product. Here, although it doesn't seem like it, the length L is indeed perpendicular to this vector R right here. Mostly because if you were to look at this from a top-down view, or I guess you could, it's more clearly visible down here by the current I. Here, the current I is traveling downwards, and the distance R is pointing this way, still 90 degrees to each other. So we can safely say that dl here is perpendicular to R. So since dl is perpendicular to r hat, we can say dl cross r hat is just equal to dl. There's no need to deal with the r hat anymore. There's no need to deal with the sine theta involved with the cross product here. It's just dl. So rewriting our equation then, we've got bx equals mu naught I over 4 pi times the integral of dl over r squared times cosine of phi. So our next problem is we probably need to figure out exactly what this cosine of phi is, because until we know what that is, we're not really going to be able to safely integrate through this function, or we're not going to be able to substitute everything that we need in. So coming back over here, we don't know enough about the components of this magnetic field dB right here. So we need to figure out how we can find this angle maybe right here. We'll call this angle theta and hope that we're able to find it. So the first thing I note is that this angle plus this 90 degree that we drew here plus this angle theta right here all makes 180 degrees. So out here, if we say that 180 minus 90 minus our angle theta, let's say, equals the angle phi, well then we can safely also say that 90 minus theta must equal phi. So plugging this in for phi within our cosine of theta here, we've got cosine of 90 minus theta, which would also say, which can convert into sine of theta. Since 90 minus an angle plugged into a trig function will always equal the other trig function. So if it's cosine, it'll turn into sine, or vice versa. Now, the useful thing in doing that is that, well, we know a heck of a lot more information about the components of this thingy of this side over here. We know the base of this triangle, which is a length x, and we know the height of this triangle, which is our distance r. And so because we know both of those, x and r, they're given information, well, we can use a simple trig ratio saying sine of theta equals opposite over hypotenuse to say sine theta being opposite over hypotenuse is the opposite, big R, over the hypotenuse, little r, right here. So we've got a couple of things to rearrange and plug into our equation before we evaluate. So what I'm going to do out here is rewrite bx as mu naught over 4 pi. And the first thing I'm going to do is I am going to take this r squared here and pull it outside of the integral. My main reasoning for this is that this hypotenuse r doesn't seem like it's going to change as we revolve around this circle. The distance x is remaining relatively constant. This distance r, the radius of the circle, remains constant. Therefore, this distance r here must also remain constant. So we are safe in taking this r squared and moving it outside the integral. Now, I'm also going to take this cosine of phi and move it outside of the integral because, again, the radius of the circle r isn't going to change, and the distance from any point on the circle to point P is also not going to change, the hypotenuse. So I will plug in r over r out here, and then we are left with the integral here, which is just now the integral of dl. Cool. Now, one last thing that we can consider before we officially evaluate and finalize our answer is that we can technically get this distance r in terms of our given information. Because, again, we know the base of this triangle x, and we know the height of this triangle r, and so with the simple Pythagorean theorem, we can evaluate what that distance little r is. So here, little r equals x squared plus big R squared. And now when we need to, we can plug this into our equation to make sure everything is in terms of the given information. So to evaluate this integral, all we need to do is take our term dl right here and integrate it over really the path of this loop here. This is a fairly trivial integral, just like if we were to integrate over d phi, because we're effectively just integrating through a full circle over the path of that circle. In other words, we're finding the circumference of a circle anytime you have an integral like this. The main reasoning for that is that we're taking a bunch of tiny lengths around the circle and just adding them all up. That's really no different from just finding the total length of the circle. So evaluating this, we can start to get to our final answer here, which is going to be mu naught I, let's say r in this case, divided by 4 pi r cubed times whatever our integral evaluates to, which in this case would be 2 times pi times the radius of the circle, big R. And of course, we can do some final rearrangements here and plug in all of our known information. And so our final answer here would be mu naught I times r squared, big R squared, I should say, divided by 2 times, and here's where it looks a little nasty, x squared plus r squared to the power of 3 halves. The last couple of things I did there was I took these pi's, I splunkied them out. I took this 2 and reduced this 4 down to 2, and then replaced little r with our Pythagorean solution over here. So this right here is our final answer. Very nice. Now it is worth noting that we can technically take this problem now, or this equation that we've gotten, and transform it into a slight variation of the previous example. I mentioned that in the previous example, we could take our original result and multiply it by 2 in order to get the magnetic field strength at the center of a complete circle. And we can technically do the same with this equation that we just derived. Say this distance x was 0. Well, in that case, our equation that we just derived would simplify down to mu naught I times r squared divided by 2 times, well, effectively r cubed. In that case, well, we have a nice splunky we can take care of here. This r squared will go away entirely, and we're left with 1 r on the bottom. And so our magnetic field strength at the center of this complete circle would be mu naught, it's the probably worst mu I've ever drawn in my life, divided by 2 times big R. Note that that is twice the amount of the answer that we got from the previous example. So it all kind of ties together in the end. Very nice. All right, so that's 2 basic examples involving loops of wire in which we kind of have to apply the Biot-Savart Law. There isn't a much easier way to approach it. There are, of course, other applications of Biot-Savart Law that are possible to see, and I may upload examples involving those in the future. They're a little bit more lengthy and require a bit more heavy calculus, so that's why I'm electing to overlook them in this video for now. But I hope this was a helpful introduction to the Biot-Savart Law. And in the next video, we'll cover a slightly nicer equation that makes our lives a lot easier. So until then, thank you very much for watching, and I hope you have a good one. Farewell.